Now, this mini lecture is going to be about refraction. Refraction is the bending of light as our light ray passes from one medium into another if they both have different indices of refraction. So the quantities that we're going to be talking about here are the index of refraction of our materials and angles that we call the incident angle and the refracted angle. Now here, this is what we're going to be working with. We are going to have interfaces again between two mediums. We've got our normal line that's perpendicular to the surface. Here we have our incident ray coming in through our first medium, and it's going to make an angle, our angle of incidence, with respect to the normal line. And then that angle gets, or that ray gets bent when it passes into another medium with a different index of refraction. And then we call the angle of refraction, this angle here, the angle between the normal and our refracted ray in the second material. So we care about the angles with respect to that normal line, that line that's perpendicular to the interface between our two mediums. Now, refraction, we see this happening in our everyday life, okay? And you see it whenever you look at like a clear glass, you put a straw in and maybe you have water in it, and you see that the straw and the bit of straw and the water are offset from each other. That all has to do with refraction. It has to do with the fact that the rays of light are bent whenever the light is moving through the water, which has a different index of refraction than air. A similar thing happened to me over Christmas, 2 Christmases ago, before coronavirus, when I was with my nephew at the aquarium. And we were looking at some seals in the aquarium, and he was like, "Oh my gosh, Aunt Maria, why does the head of the seal look like it's off? It's broken from the body of the seal." And then we were able to talk about the index of refraction at the aquarium. In 1621, the Dutch scientist Snell proposed a mathematical statement of the law of refraction that we call Snell's law. Snell's law describes the refraction or the bending of light as that light passes through a different medium. And that equation here, N1 sine theta 1 equals N2 sine theta 2. We're going to work on that equation next. We're not going to derive Snell's law here, but Snell's law is derived by finding the quickest path that light can take, or the shortest light travel time, the quickest path that light can take inside a medium. As we talked about how actually the index of refraction is defined by the ratio of the speed of light in the vacuum to the speed of light inside a material that has an index of refraction that's different than that of a vacuum. But we're going to use Snell's law here in order to solve a couple of problems next.
Let's think a little bit more about Snell's law and how our angle gets refracted when it enters into a different medium. So here I have an interface between two materials. On top, I've got something with an index of refraction that I'm going to call N1. On bottom, I have something with an index of refraction of N2, so this line is the interface between those materials. Okay, so you see my ray of light has an arrow. That ray of light tells me the direction that my light is coming. So my light is coming in this way. It encounters the interface between the materials, and then it gets refracted, bent, in the second material. Okay, so since the ray is coming in to the interface through material 1, this is our incident material. This is our incident ray, and this is our incident angle here. Okay, so here I've got my vertical dotted line. That's my normal line, perpendicular or at right angles to the surface here, 90 degrees. So our incident angle, I'm going to call that theta 1. My refracted angle, this is theta 2. okay? And these angles are always the angle between the ray and the normal line, okay? It's never this angle, it's never this angle, it's always the angle between my normal line and my ray for the incident angle and the refracted angle. Okay, so here I've got Snell's law. Let's see what happens to our angle of refraction if N1 is less than N2. N1 is less than N2. Let's say this is air, maybe this is glass or water. If N1 is less than N2, that means that our incident angle theta 1 is going to be greater than theta 2, than our refracted angle. Well, why is that the case? Well, let's look over here. We have to have N1 sine theta 1 equal N2 sine theta 2. So if N1 is smaller, N2 is larger. In order for both of these sides to equal each other, if N1 is smaller compared to N2, that means that this term, sine theta 1, has to be bigger, okay? And for all angles between 0 and 90, as the angle theta increases, sine theta increases. So if the index of refraction N1 is smaller, my angle theta has to be bigger, okay? So in this case, if let's say this is air, this is water, index of refraction is smaller here, bigger here, my refracted angle is going to be smaller than my incident angle. And you can always use that to double check yourself when you're working on a problem. The opposite happens if N1 is greater than N2. So if N1 is greater than N2, that means that theta 1 has to be less than theta 2. Okay, so let's say we swap the materials. Let's say N1 is now glass or water. N2 is now air. Okay, so if this index of refraction is greater than N2, and this is our incident material, if the material through which the ray of light is moving through first has a greater index of refraction, its refracted angle theta 2 is going to be bigger than its incident angle theta 1. Okay, so if N1 is greater than theta 2, incident angle has to be less than our refracted angle. So you get refracted more strongly if you're moving from high index of refraction to low index of refraction. We're going to apply Snell's law now inside a slab of glass. So here we have a thick slab of glass. It's not a thin film. It's much thicker than the thin films we were talking about previously. And so on all around it, on all the other sides, is air. So we've got our slab of glass in air, okay? And we're going to have a beam of light that is incident on my slab of glass. So the incident angle right here, I'm going to call that theta 1, that angle with respect to the normal line. It's going to get refracted when it enters into the glass. It's going to get refracted when it exits out the glass, okay? So I'm going to call this angle down here theta sub 3. This is the angle with respect to the normal line that my ray of light has when it exits out of the slab, and we're going to call this the refracted angle when it exits the slab. So we are going to show that the angle of refraction of the emerging beam, which I'm going to call that theta r, okay? So we're going to show that the angle of refraction of the emerging beam down here is equal to the incident angle of the incident beam. So up here, this is my incident angle of my incident beam. Okay, so you could call that theta I. So for this particular problem, we are going to show that the angle of refraction of my emerging beam is the same as the incident angle for my incident beam. All right? So in order to do this, show that problem, we're just going to start working the problem. Pretend as if I asked you to figure out what was this angle of refraction of the emerging beam, and I'm going to give you what my incident angle theta was, and then we're just going to work toward the problem, and hopefully we end up having both of these numbers match. Then the only other pieces of information we know is that the index of refraction of the slab of material is 1.5, and then that means that the index of refraction all around that slab is 1. It's just air. Okay, we said that when we set up the problem. Now, the incident angle for this ray of light, we're just going to give it a number. We're going to say that that incident angle is 30 degrees. And now we're going to work through the problem and figure out what is this refracted angle when my ray exits out here on the other side of the slab, and hopefully that also equals 30 degrees because that's what we're asked to show. So how are we going to do this? Well, we have to apply Snell's law twice. We have to apply Snell's law at the first interface, and then we have to apply Snell's law at the second interface. So let's apply Snell's law at our first interface up here. So we've got N1 sine theta 1 is equal to N2 sine theta 2. We know both of the index of refractions for this interface here. We know my incident angle 30 degrees, so we're going to try to solve for this angle here, what I'm calling theta sub 2. This is the refracted angle after my ray of light passes through this first interface. So I'm going to solve this equation for theta 2. So I do that. I'm going to divide both sides by N2 first. Okay. So sine theta 2 equals N1 over N2 sine theta 1. Now, if you remember from last semester, how do we get that angle by itself? Right now, it's just sine of the angle, okay? To undo the sine, essentially, we take the inverse sine of both sides. So the inverse sine of a sine function gives you back the angle here. So, well, I'll just say inverse sine of sine theta just gives you back the angle theta, okay? So, and that little superscript sub 1 tells you that's the inverse, okay? So theta 2 is equal to the inverse sine of N1 over N2 sine theta 1. Okay, so theta 2 is the inverse sine of N1, which is 1, over 1.5 times sine of my angle 30 degrees. That's my incident angle. That's also what we call theta 1 here. Okay, so in order to do this, you need to do two things with your calculator. Oh, there's two options for you. You can either be sure that your calculator this time is in degree mode, and in which case your answer is going to come out in degrees. Or you could put your calculator in radian mode, but then you'd have to convert your angles from degrees over to radians. Okay, to convert an angle from degree to radian, you multiply that angle in degrees times pi over 180. So you're going to have to swap and pay attention what mode is my calculator in. So if we're dealing with degrees here, maybe let's just keep our calculator in degree mode, okay? So you have to take the inverse sine of 1 over 1.5 times sine 30 degrees, okay? Again, you have to be super careful about how you input this stuff into your calculator, okay? So if you're going to input this into your calculator, you would have to do the inverse sine, and then you'd get this open parentheses here. And then, if you're going to type all this into your calculator at once, if you're going to do 1 divided by 1.5, you would need to put parentheses around the 1 divided by 1.5. Then you multiply it by sine of 30, and then you close that parentheses, and then you close that parentheses, okay? So you have to be super careful. You find that the angle theta 2 is 19.47 degrees. All right, so that is my angle of refraction when my light passes from air into glass. Okay, does that make sense? So we just went through all that trouble earlier thinking about the angle of refraction versus is your index of refraction larger or smaller. So here we have a larger index of refraction in the second material. That means our refracted angle, our angle of refraction, has to be smaller than our incident angle. And it is. Our refracted angle, 19.47, is smaller than my incident angle, 30 degrees. So we are true to Snell's law. Okay, so we've got this. You could stop, so just this part right here, just this one interface using Snell's law is one workbook problem, one kind of workbook problem for you, okay? Now we're going to keep on going, okay? Now we have this angle of refraction. We have to use that in order to figure out something about the final angle of refraction when it exits the material. Okay, so here we know what this angle theta 2 is. We just calculated it. We've got to figure out what is this angle right here, okay? Because this angle right here is going to be the incident angle for this interface here for us to use Snell's law a second time in order to get this refracted angle here, okay? So if you remember from geometry, we've got a lot of geometry in the geometric optics part of this class. So we've got two parallel lines right here. Two parallel lines, and we've got a line that's intersecting them, okay? So here we have what we call alternate interior angles. Alternate interior angles are congruent. That means that they're equal. So when I've got these parallel lines, I've got this ray sort of intersecting them. That means that this angle theta 2 is the same as this angle here, theta 2. Okay. So now for my second interface, we're going to use Snell's law a second time. Here's my second interface. This time I've got N2 sine theta 2 equals N3 sine theta 3. Okay. And we need to get at this angle theta 3. That's my angle of refraction when this ray exits the material through both of those interfaces. So I've got to solve this equation for theta 3. So just like we did up here, sine theta 3 equals N2 over N3 sine theta 2. So theta 3 is equal to the inverse sine of N2 over N3 times sine theta 2. Okay? So this is the inverse sine of N2, 1.5, over N3, which was 1, times sine of theta 2. We saw that that was 19.47 degrees. Okay. So if we do this calculation, we find that theta 3 is going to be equal to 30 degrees. Okay, so in the end, we showed that theta 1 is equal to theta 3, and they're both equal to 30 degrees. And that's the same thing as saying that our incident angle is the same as our refracted angle when that ray exits out of the slab. So we did our job to show that that statement was true. Okay, so that's how we work through one of these show that problems. Now, were we true to Snell's law over here? Let's double check. So for this interface, N2 was greater than N1. So if N2 is greater than N1, that means our refracted angle has to be greater than our incident angle. And our refracted angle of 30 degrees was bigger than our incident angle at this interface of 19.47 degrees. So we stayed true to Snell's law. So in your workbook, you're going to have a problem where you only have to deal with one interface, like the first part here, and then you're going to have another problem where you have to deal with both of these interfaces, okay? And in that particular workbook problem, you might not have air, glass, air. You might have air, glass, oil, or you might have air, glass, water. You know, you might have different indices of refraction than what we just did right here.